Thanks, Tony. Next up, we have David Maltz from Microsoft Research, who's going to be presenting on data center challenges, building networks for agility.
So hi, thanks. I'm Dave Maltz, and to be clear, I'm talking about the work of many, many people inside of Microsoft, both Microsoft Research and some of our product groups as well. What I'd like to do today is talk a little bit about what goes on inside some of our mega cloud data centers, based on some industry studies we've done of our data centers as well as some other data centers, basically the cost, the pain points that we're seeing, although I think that the previous talk was in some sense an excellent setup for the problems and pain that a lot of us are experiencing. And then I want to talk about VL2, which stands for Virtual Layer 2, a technology for building data center networks that's designed to alleviate a lot of those pain points. Basically, we think we're going to provide what data center tenants and data center owners want, the ability to virtualize networks inside of these very, very large data centers, while still providing uniform high capacity between all servers in the data center, as well as performance isolation so that one tenant can't knock down another tenant. And finally do this while decreasing costs and making it easier to manage the whole thing. I'll show you some of the principles and insights behind VL2, and because every project needs at least 3 names, you've seen VL2 referred to in other places as Project Monsoon. And finally, I'll circle back and tell you some about the VL2 prototype and evaluation that we've done of it. So a little bit about what is a cloud service data center. Well, from the outside, it looks like a building. Inside, we've got power, router, fiber, servers. The interesting thing about cloud service data centers, or mega data centers, is the scale at which they operate. Effectively, what we're trying to do is leverage economies of scale. So we'll go into a site, we'll say, all right, how big of a data center can we build here to maximize the economies of scale? Usually what we're limited by is how much electricity we can get to that site, and then we build out there. So typically these things are going to have about 50 to 200,000 servers as they're built today. Those servers are, of course, divided up among hundreds of different services. These are not all doing the same thing. They'll be running Messenger, Hotmail, search, different parts of search as well. And the key thing here that makes this work is that scale is paramount. That some servers use very small numbers, some services use only a few servers, some of them use thousands and thousands. Now, where do the costs in these data centers come from? Well, here's a table that looks down at the breakdown. The first thing to notice is that the most expensive thing in that data center is actually the servers. The academic environment, a lot of people are worrying a lot about electricity and power. And as you can see sort of over here on these, this isn't going to work well. As you can see over on the pie chart, power is a significant fraction, but servers still make up about half of the total cost of running a data center. And those costs are significant. So if you want to think about a data center, you should really think about them as being like a factory. And the number one goal is to effectively maximize the amount of useful work that we can do per dollar spent. Well, okay, really, of course, you want to maximize revenue per dollar spent because that's profit. But I'm a technologist who understands infrastructure, not someone who can invent cool new applications. So this is what I'm going to set out as the challenge for us in the infrastructure space. The ugly secret, of course, is that if you look across many large data centers, 10 to 30% CPU utilization is generally considered good. There are a lot of servers that are sitting there not doing anything at all. And the reasons for that are fairly complex. But effectively, it boils down to the fact that reassigning servers among services is very hard. And we'll talk some about why that is in the next couple of slides. We also heard about that in the previous talks. But because reassigning servers between services are hard, basically every service is convinced that their service is going to hit it big. And when they hit it big, they're going to need a lot of servers to handle that capacity. No one wants to have a success failure where you become popular, but because you don't have enough capacity, your response times go up and users flee from you. So everybody wants to hoard servers so that when they hit it big, they have enough capacity to handle that. Effectively, the only way to work against this and sort of increase the ROI is to add what we call agility, the ability to take any server and apply it to any service. And that server has to be able to come from anywhere in the data center. So what does a network of modern data center look like? It's probably familiar to lots of you. Effectively, typically have the internet at the top, going down through a layer 3 aggregation and switching, aggregation and routing layer, down to what we call pods. So inside of a pod, typically layer 2 switches. Again, you'll see a lot of redundancy. Okay. Down at the bottom, we'll have racks, typically 20 to 40 servers per rack. A top-of-rack switch at the top of each rack, typically dual uplink to servers. Now, this whole thing is, as you can see, sort of a hierarchical network, and it's designed for 1+1 redundancy. So where we use switches, we use them in pairs. Where we use routers, we use them in pairs. The equipment in the higher up in this hierarchy is handling more traffic. Basically, traffic density increases as you go higher in the network. So this is what we call a scale-up philosophy. As we get higher and higher in the network, we're using bigger and bigger iron routers that can handle more and more traffic density. Because they're handling more and more traffic, that means a failure of either of those devices would be much more impactful. And so we spend the money to get larger and larger, more and more reliable devices. And we'll see an implication of that in a few moments as well. And then, of course, the mix of links that we're using. Typically, we're using 10G. Once we're off the rack level, the uplinks from our TORs are either 1G or 10G. And these are designed, again, to give you that sense of scale. We have about 4,000 servers or so per layer 2 domain. So to get out to a 50,000 data center, as you can see, we have many, many of these layer 2 domains. Now, one of the reasons that one of the problems the network causes for us is basically keeps us from dynamically growing and shrinking servers the way we want. Let's say we have a load balancer, labeled as LB here, which is spreading traffic over the racks that are shown in green, which might be the servers for one property. Now, if we need more capacity to handle those sets of servers, handle the workload for that service, we might want to reach over and recruit a rack that might be idle in another layer 2 pod. But effectively, we can't do that today because our load balancers make it very hard to do that. It's actually a couple of things that are going there. Load balancers typically want to spread traffic over servers that are in the same VLAN beneath them. Because IP addresses are topologically determined by the access routers at the top of each pod, if I want to grab a server from another pod and deploy it to a service, that means it's going to have a different set of IP addresses. And IP addresses are just found everywhere. They're found in everything from asset management to security certificates. So in order to include machines that have a different set of IP addresses into an existing service requires a lot of retooling. Sadly, a lot of that is manual and very error-prone, and it takes a long time. Another big problem we have with our network today is there's not enough performance isolation. VLANs, when we use them inside of our layer 2 to isolate two properties or two services, provide reachability isolation only. They'll keep the purple servers from talking to the green servers, which would be something we might want to have happen. But if the purple servers are having a bad day, they're either being DOSed or somehow generating huge amounts of traffic, there's nothing in the layer 2 configuration that keeps that traffic from stomping out the traffic coming from the green servers. Finally, basically because we're using a scale-up philosophy, as you go higher and higher up the network, there is less and less capacity available per server. We effectively see oversubscription factors of 10 to 1 or worse. And honestly, it's more like 80 to 1 or 240 to 1 as you have to go through the highest layers of the network. So even if we could take servers from the same service and put them across different pods, we probably wouldn't want to do that because the servers that are far away from sort of the mothership installation are going to see very bad network performance, and that can actually drag down the performance of the entire service. So we effectively sort of have to keep everything together the way our networks are built today. The reason this is becoming so important is because there are actually two main kinds of applications that run in our data center. One of them is what you might think about, serving web pages to user. That's outward-facing traffic. That traffic typically comes in from the internet, goes down to servers, goes from servers out to the internet. But actually about 80% of the traffic in our data center today is of the second kind. It's internal computation. It's things like generating search indices, looking for ad relevance, finding ways to actually mine data to improve the value of our services to users. And we see that mix actually moving towards more and more internal communication over external communication. And finally, if we actually were to enable agility, where we effectively could take any set of free servers anywhere and apply them into any service, we'd end up with a deployment that might look something like this, a whole bunch of servers spread out all over our network. And that basically means that traffic engineering is going to be an absolute nightmare. If we wanted to do any type of quality of service guarantees or do any explicit manipulation of link weights, explicit manipulations of link bandwidth, in order to make sure that some service has good connectivity between servers, it would become a hopeless task because basically it would be too dynamic an environment. To put some numbers to this and quantify it, we went out and measured traffic in a relatively large, well, actually small by some scales, but a 1,500 server cluster. Those 1,500 servers are divided among about 80 racks. What we effectively did is on the servers, we logged the 5-tuple of every socket, send and receive that those machines were doing. Took that, aggregated it, looked at the flows, looked at the traffic matrices inside of that, and then looked at how those traffic matrices evolved over time. And this is basically what we saw. So the top graph looks at the distribution of flow size. The red line shows how common are flows of different sizes. And what it effectively shows is that the vast majority of the flows in these data centers are small mice. They're relatively small, around 100 to a few thousand bytes. And this is typically sort of heartbeats, management control, very bursty traffic. However, something that's interesting is that most of the bytes in the network, which is what this blue graph shows, are actually part of flows that are 100 megabytes or larger in size. An interesting thing is that this is not what you typically see on the internet, where you see such a great dichotomy. Internet, you often see a much sort of smoother mix of flow sizes. The data centers being an engineered environment, we tend to see these kinds of extremes. One other thing that we see is that there is a fair amount of communication among the servers in the data center. The median server is talking to 10 other servers at the same time, and it has a very, very long tail as we're doing map-reduced computations or things where large amounts of information is being aggregated together. One of the things we wanted to do was see how volatile the traffic inside of our data centers are. So what we did is we actually took these traffic matrices and we clustered them using a technique that Ian at University of Austin put together a few years ago. And effectively what you can see here is this is showing basically how good of a fit we have for using a varying number of clusters. There's sort of a knee here around 40 to 60 clusters. And what that says is, all right, if you use 40 to 60 clusters, you wouldn't be doing too bad at sort of representing these traffic matrices. But you can see that as I use more and more clusters, then I effectively get a better and better fit. What that means is that tells us right there there's a lot of change going on in these traffic matrices. It's not like we're switching from a night pattern to a day pattern or even an hour pattern to an hour pattern. If I go in and I look and say, all right, let me take 40 different clusters and now look at how those clusters evolve over time, what you get is this Rorschach's diagram, where effectively there is no particular pattern. If I start looking at how long I stay in any one particular traffic matrix, we see that basically up to the 80th percentile, 80% of the time, I stay in the same pattern for only 100 seconds. And then I switch to some other completely different traffic pattern. And at the 99% of the time, I stay in a traffic pattern for no more than 800 seconds. Finally, what we wanted to do is basically see is the network a bottleneck? What we did is we showed the intensity of communication from one server to another server over a period of time. And effectively, color indicates how much traffic was being exchanged there. And what you can see is that most of the mass is on the diagonal. Now, why is that? Because the diagonal is effectively the set of servers that are all connected to the same top-of-rack switch. At the top-of-rack switch, there typically is an oversubscription. And so that's great. In fact, a lot of people work really hard right now to place all the servers that need to communicate under the same top-of-rack. And they generate immensely complex optimization and placement algorithms in order to do that. But what we can see is all these stripes, horizontal and vertical. That's basically showing that servers do need to communicate with servers that are off-rack. And as you can see by the color indication, those communications tend to be slow. And those are the long poles that actually slow down the whole application and keep the determine what the time for the application to complete is going to be. Finally, coming back to the notion of faults, we looked at faults in our data center. And as I mentioned before, we need very high reliability near the top of the tree. That's very hard to achieve. As one example, we had a temporarily unpaired switch, a router fairly high up in our tree. It was unpaired because the other router in the pair was going down for maintenance, and the unpaired router failed. And that caused an outage that took us 4 hours to resolve, and there was an actual outage for about 10 million users during that period of time. What we effectively found was about 0.3% of failure events knocked out all members of a network redundancy group. Now, typically, thankfully, these strike low down on the tree, basically like a Tor losing both of its uplinks. So the impact is not great. But effectively, the message is that if you want to be running 4.9s or 5.9 network, and 0.3% of the failures are wiping out all of a network redundancy group, and they can strike anywhere, this sort of 1+1 redundancy is just not going to work. Instead, we step back and look, okay, what objectives? What do we want our data center to do? And as you heard described just before, effectively developers want network virtualization. They want to think that all their servers and only their servers are plugged into their very own Ethernet switch. The reason they like that model is because, one, it provides uniform high capacity. Basically, the amount of traffic I can get between any two servers is limited only by the speed of their NICs. And when I want to go add another server to an existing service, I don't have to think about where it's coming from. Right? I can just grab any free server anywhere in my data center and use it. Two, this model provides performance isolation. If each service really, it's like they have their own Ethernet switch, then they don't have to worry about the traffic that another service is moving, impacting them. And that's critically important. And finally, the notion of layer 2 semantics. Developers really do think that they can send broadcast packets in order to do discovery. They think that they want to use flat addressing so they can bring their own address space if they're migrating an application from, say, an enterprise data center into a cloud data center, or they just want to encode some extra information into the IP address. It makes it very hard for us to tell them what IP address they want to use. So in VL2, we use the following design principles to try and meet the objectives on the previous slide. We saw that there was so much volatility around, so we basically threw up our hands and said the one thing that can deal with all this volatility is actually using randomization. So we're going to use randomizing techniques and randomizing algorithms. We're actually going to separate names from locations because that's going to allow us to get this flat naming space that will make it easier to do agility and apply any server to any service. And we're going to leverage the strengths of end systems. Basically, we're going to use the fact that end systems are programmable and they have big memories in order to make this work in a reasonable fashion. And finally, we're going to try and build this network using only the components that are actually available right now so that we can actually, well, have something that we can test, that we can use, and that we can deploy with today. So why is this an interesting time to be sort of working with this kind of thing? This slide here is actually a little bit dated, and I'll tell you why. One thing that is really important is that there are basically low-cost switches becoming available that are very, very fast in terms of port count, very high port count, and very high aggregate throughput. So generally, these are based around ASIC switch on a chip, things from like Fulcrum or Broadcom. They tend to be cheap because, you know, this is the switch. This is a picture of a switch that has 20 ports of 10 gigabit Ethernet. This particular one has CX4. A lot of them have SFP Plus now. And as you can see, there's really nothing on the motherboard except for traces to that switch chip. So that thing really does have 240 gigabits of capacity inside of it. The list price is $10,000, and street price is a lot less, as you might imagine. One of the reasons it's so cheap is because it typically has small buffers. So this machine is going to have about 2 megabytes to 4 megabytes of packet buffer on it, as compared to some higher cost parts that are going to have much larger buffers. And it's going to have small forwarding tables. This thing's going to have on the order of 10,000 or so V4 routes or MAC addresses in it. One thing that is true is that it's a fairly flexible environment. Oops, keep hitting the wrong buttons. This is basically a general purpose processor that you can actually program. Now, when we first started the project, we thought, well, this is great. We're going to build our own control plane software, and we're going to run it on these switches. And what we actually found is that, well, our operations people told us that we were nuts if they thought that they were going to run a network running our experimental control plane code on it. But effectively, what this structure for the hardware has meant is that you can get basically any layer 2 or layer 3 protocol running on these devices at about the same cost. The difference between a layer 2 and a layer 3 switch in these kinds of devices has basically disappeared, and the pricing differential is also disappearing. The final other thing that means that we can do this now is the notion of centralized coordination is not scary in mega data centers. Basically, we already have centralized services that managing the provisioning of servers, of these servers, that manage the health model and watching, make sure their servers are healthy. So adding centralized services that are going to coordinate the network across these devices is something that's acceptable in our environment. Now, how do we actually go about structuring a network? There are a lot of topologies that we can use. This is the one that we've found works particularly well in our environment. It's called a CLOS network. Effectively, what we're going to do is we're going to have servers connected up in the top rack switches. That's pretty common. We're going to dual or quad uplink our top of racks. That's pretty common. But then what changes in here is sort of what would be in the network cage of the data center. We have these aggregation switches, which are not connected to other aggregation switches, but are connected to each of the intermediate node switches. We often call these AG switches the A switches, and these intermediate node switches B switches, or bouncer switches, for a reason that you'll see in a moment. The total number of servers that you can connect is a function of the degree of these switches. Now, what's going to happen is that we're going to use a technique called Valiant Load Balancing to actually spread traffic across our network. Effectively, if a server wants to make a flow to another server, what we're going to do is we're going to pick a random path through the network in order to do that. The reason we like this, sorry, every time I touch the mouse pad, I get a forward. I know how it is. One other thing that's nice about this topology is that if you look at the bisection bandwidth, basically the amount of capacity going between each of the layers, it's the same. So effectively, we can build a network that has no oversubscription in it. Because we have so much path diversity, so many different ways to get between one server and another server, we effectively have resilience. So in this network, if I lose one of these intermediate switches, and I had a total of n of them, I've lost 1 over nth my capacity, rather than losing half my capacity. And effectively what that means is I can start using recovery-oriented computing philosophy to actually manage these switches. I can basically build a health model for a switch, and if the switch sort of looks like it's not behaving right, at very low cost, I can just decide to reload that switch. And that's often enough to push the switch back into a healthy state. Whereas if I have that hierarchical design where I have routers working in pairs, you know, it can take 20 minutes for a large device to actually reload. And if I only have 2 of them, reloading the switch creates a 20-minute vulnerability window in which a second failure could actually have a very large impact. Sorry, going back to this slide now. Now, how are we going to actually use this very densely connected backbone? We're going to use a technique called Valiant Load Balancing as a traffic engineering philosophy. Effectively, if I want to run a flow between 2 servers, I'm just going to pick a random path between them. I'm going to pick a random one of those bouncer switches to basically bounce the flow. So if I had several flows between 2 servers, they might all take different paths for the network. The reason for doing this is because there's actually a mathematical foundation that shows that this will be provably hotspot free if you do this type of randomization. And it actually works really well in practice, we've found. Now, how are we actually going to get that type of bounce pattern if we're using these cheap, fairly dumb switches? Well, effectively, we're going to use encapsulation as a trick. What we're going to do is we're going to have the servers, when they send each packet, add some extra headers to it, which is basically going to just standard IP and IP encapsulation style, for example. Say, this is a packet that's going from some source to some destination, but the outermost IP header, or the outermost header, is going to say, first, go to this intermediate node. And then when the packet gets the intermediate node, it's just going to do a line rate pop operation, pop off that outermost header, exposing the next inner header, which is going to say, okay, deliver this packet to the top of rack switch to which the destination is connected. The top of rack pops off that header, and down it goes to the destination. And there are a lot of different types of encapsulation available. The same type of trick can be used with any of them. The one that we found works particularly well are variations on IP and IP and sort of MAC and IP. Now, where is that sort of routing information going to come from? How is a source, when it sends packets, going to know what sort of packet headers it should encapsulate onto the front? Here's where we leverage the strengths of the end systems. Effectively, what I'm going to do is when I have an application that's going to send a packet, it's going to look at its forwarding table. It's going to say, oh, I'm sending to someone who's on the same subnet as I am. So the TCP stack, normally, just as normal, is going to try and generate an ARP. What we're effectively going to do is with a shim driver at the endless layer, using Windows terminology, we're going to trap that ARP. We're going to bounce that up to a usual layer process we call a VL2 agent, which is going to do a lookup off to some logically centralized directory system. The directory system is going to say, well, I know where that IP address that you're trying to talk to is, and here's all the information you need to encapsulate the packet when you send out. We send that back, and now all future communication to that destination is going to, doesn't have to pay this lookup penalty. Where does the directory system get the information from? Well, it's in cahoots with the provisioning system that actually put that VM or put that server image out there on the server in the first place. Adding extra kernel drivers to network stacks may sound like a scary thing, but the OS that's running inside data centers is already very heavily customized. Effectively, people have extra support in there for VMs, extra support for blob file stores. So putting this type of network driver into the stack, we haven't had any resistance to. The end result of this, though, is that applications can work just in terms of what we call application addresses, AAs. These are flat names. Any of the IP addresses actually used by the network infrastructure, by the switches themselves, can be completely hidden. They have, because we've sort of replaced ARP with this directory system lookup, We're providing this layer 2 virtualization. It looks to them like they're on a VLAN with anyone that the directory system thinks or says that they should be on a VLAN with. The final question is, how do we actually sort of make this host-based encapsulation play nicely with the network fabric, which has to be able to change in order to deal with topology change? What we found is that it actually works best to push layer 3 all the way down to our top-of-rack switches. So effectively, in the simplest design, we are running an IP fabric inside of our data centers. Here I've shown on the bottom the top-of-racks, then the A switches, and then the B switches above those. So simplest design would be to just use something like OSPF with ECMP. Basically, what that would mean is that if a server X wants to send a packet to a server Y, it would prefix the packet with the address of the top of rack for Y and let it go, and ECMP would use the whatever paths are available to deliver the traffic. Turns out, though, that a lot of these cheap switches actually are optimized for up-down routing, which means that you can go in through the front panel and back out through Uplinks without any oversubscription. But if you try and cross through and go through front panel links to other front panel links, you can actually hit some internal limitations of the switches themselves. So we've actually found it's desirable to actually push all the traffic up through the bouncer switches, even if it could do early turnaround at various points in time. Effectively, what that means is that when we want to encapsulate, we want to have this extra layer of encapsulation on the front of the packet that says, I want you to go up to one of these bouncer switches. The question now is, okay, of the bouncer switches, how do I pick? I could just put that as part of the encapsulation information in the packets I send. But let's say one particular flow chose to use, say, intermediate node switch 1, but intermediate switch 1 failed. I would then find myself in a world where I have to go tell 100,000 servers or even more of that VMs that they need to update their information. And that type of state update problem wasn't tractable. So again, what we do is we leverage some nice primitives provided by L3, and we use Anycast. We effectively give all of those intermediate switches the same IP address. That means that the encapsulation can be done to that Anycast address. And as a result, effectively I get the following. Any of the blue paths are going to be used for traffic going up. Any of the red paths will be used for traffic going down. And sort of this combination of Anycast and flow-based ECMP is a very cheap way to implement a kind of Valiant load balancing that I was telling you about, where any changes in the network are actually hidden from changes in the servers. So we've actually built this. We've built this with 40 servers, 80 servers, and 300 servers. As we've gotten bigger and bigger, we've seen nearly perfect scaling. So far, we're confident that this design actually is going to scale out and keep scaling out as predicted. Just to give you some quantitative data, there's papers that I'll have pointers to with more information. But effectively, when we try an experiment, we do say to all-to-all shuffle. So I'm going to have, in this case, 80 servers, each of them trying to move 500 megabytes to the other servers. This is a nice traffic pattern to test a network with, because sort of all other traffic matrices are a subset of this one. If you can handle this one, you do pretty well on just about any. And effectively, what we see is that we're getting within about 94% of the best that we could do. And what we're charging ourselves there for is we are charging ourselves for sort of the extra bytes that we're spending on overhead, because we are adding some extra IP headers to that. So we're charging ourselves for that. That's actually a large fraction of the 6% that we're down from optimal. Most of the real sources of our inefficiency that we're actually not charging ourselves from comes from the fact that the line cards, the NICs, and our servers you'd expect them to be full duplex, but it turns out they're not. They can actually, sending plus receiving is about 1.8 gigabits a second rather than 2 gigabits a second. So some issues like that. We looked to see if VL2 actually gave us good performance isolation. We found that it did. Effectively, in experiments like this, we set up one service with a traffic pattern, then we have another service that's sort of running on the same racks as the first service, ramp up the amount of traffic it's sending and ramp it down. And what we see here is this black line stays steady. So there's effectively no impact on that between one service and another. We tried challenges where we basically do bursts of traffic, very bursty traffic. And again, we didn't see any impact on the service that we were stressing. And finally, we ask ourselves the question of basically, well, this Valiant load balancing, it's got to be giving up something, isn't it? And so we compared using Valiant load balancing, which is an oblivious traffic engineering philosophy, against some other ones. Basically, adaptive, the red curve that's shown here, says, let's say I had an oracle that would tell me what the traffic matrix is going to be for the next 5 minutes. And I'm going to run a linear program that's going to find the most optimal routing possible for that traffic matrix. And then I'll use that traffic matrix for the next 5 minutes. And the green line, best oblivious, would say, I get to know what tomorrow's traffic matrix is going to be right now, and then I can run my linear program and optimize for it. The red line, the blue line here shows what VLB did. And effectively what we're seeing is that the most heavily loaded links in VLB are up to maybe 20% more utilized than they would be if you had these Oracle-based systems that knew exactly what the traffic matrix was going to be and could optimize for it. And our sense has been at that 20% sort of potential performance loss, maybe you could have fit an extra traffic onto these links, is probably not a significant deal compared to the fact that this is a traffic engineering philosophy that's just going to work for any traffic matrix. If you have questions about how this compares to other work, I'm happy to talk about those. And in summary, going back to the beginning, the key to having an economic data center is this notion of agility, that you want to be able to take any server and apply it to any service. Tenants demand it. Owners need to provide it if they want to stay in business. And today, the network is actually one of the largest blockers that we have to achieving that because it doesn't let us redeploy servers and configure them as flexibly as we need to. Our argument is that the right model we want the network to provide is that of a virtual layer 2 per service. That means that it has to have uniform high bandwidth, performance isolation, layer 2 semantics. And with VL2, we're able to achieve these by using a whole combination of techniques to basically get that uniform high bandwidth and performance isolation. We're using Valiant Load Balancing and a network with no oversubscription. To get layer 2 semantics, we're using this name location separation trick and some changes on the end hosts. And because we are sort of changing software on the hosts that are very easily programmed, and we're using existing devices and existing routing protocols, this is something that we can actually deploy at scale right now. And so far, the experiments that we've done look very promising, and we're trying to take this bigger as soon as we can. So thank you very much.
Got a couple moments for questions if anybody has any.
I'll be okay.
Joe Provo, ITA Software. Just to clarify, the shim is only applied for the inner data center traffic, correct? And anything going external to the data center is not twisted through that shim.
Exactly. Sorry, I should have made that clear. So our network is actually connected up to sort of the interdomain routers, which do BGP speaking. And so yes, traffic that's egressing the data center doesn't get encapsulated, just goes straight out onto the internet.
So a quick question here. So
Who are you and where are you from?
I'm Paul M. Hagen from Alcatel-Lucent. So a quick question. I noticed a lot of this actually looks very familiar to what we've been working on in the IEEE for quite some time with 802.1 AQ. I was wondering if you had looked at it. You're shaking your head yes, so I assume so. And how do you see the references? Because that's exactly the reasons, the models we're looking at. When you did your test case for scale, for example, how many servers did you actually look at in the scale and the flexibility of being able to move across different virtualized domains?
So effectively, the nice thing is because we've basically punted off to the centralized directory system.
I can barely hear you.
Sorry. Because we've punted off to the centralized directory system, we don't have a scaling limitation in terms of how large a single virtual layer 2 VLAN can get, nor there's effectively no limit to how often you switch servers back and forth. So we've done stress tests where we've basically made VLANs that go up to, say, 100,000 servers. At the same time, we have things down with 10 servers, and we can basically rehome things between VLANs or sort of change the information in the directory system at about 10 millisecond granularity.
Okay, so what's your measure of scale then?
So our measure of scale is basically going to be how many servers or VMs can we get put into a VL2 VLAN, and how frequently, how rapidly can we update those mappings and have all the servers actually obey the new information.
Okay, and then how many would you actually see running in a given environment? Like how many virtualized layer 2 environments? Instead of saying VLAN, we're really saying...
Yeah, yeah. How many virtual VL2 environments? In some of the environments that we're looking at, it's tens to hundreds of thousands.
Okay. So the reason why I ask, obviously, I'm not trying to really lead you down the primrose path. It's just as we were looking at this in the IEEE, you're obviously looking at the exact same kind of views, right? Because we're not only looking at data center, we're looking at enterprise as well as the metro environment, all right? So what we use is in fact, I found it interesting that you use an IP and IP encap where we use a MAC and MAC encap. So we have complete backward compatibility, and then we get the benefits of silicon for Ethernet switching. And the flip side is that we realized that VLANs would not scale, right, and the mapping. So there's a new field available, and we call it in the 802.1 AH, it's commonly known as PBB, is the ISID value, and that gives us 16 million possible services within any environment. And then instead of trying to invent a new protocol, we just use ISIs to replace spanning tree. And that's the whole intent of what we're working for, just basically let's eliminate spanning tree and get rid of that hack and move to an actual IGP-based way of controlling the environment. Right? So when you were looking at this, did you look at a way of actually seeing the entire topology and being able to move? I'm going away from Mike. Or was it more about containing particular groups of servers, giving how you're doing your IP reachabilities?
So we are not interested in warping entire topologies. Basically, infrastructure is going to stay stable. The fabric stays stable. We are basically seeing motion at the leaves.
Okay, thank you.
Okay, a couple more, and then we'll move on.
Todd Underwood, Google. So one of the things in the motivators of this that I didn't really understand was there are all these separate tenants that are all, as I understood it, Microsoft, who all work for the same company, but who all have completely divergent software stacks and uncoordinated resource utilization, and that's why. Because this seems like a great technology for a common data center operator among disparate companies that have no system of coordination or communication, but you describe this sort of federation of chaotic competing interests inside of what I believe to be a single corporation. And that so the whole motivation of this inside of Microsoft confuses me. It's neat technology, but I don't understand why you need it.
Okay.
I understand why other people need it, but why do you need this?
That's a fair question. One is if you can handle that more chaotic environment, you can handle everything. So, and a lot of people don't appreciate sort of the scale that Microsoft has. Microsoft has mega data centers on every continent. We actually have, we're up there equivalent, basically the same kind of scale that Google, Yahoo, Amazon all have. The other thing is that in addition to hosting our own properties, we have a number of services which actually we are hosting, outsourcing for various enterprises. Our business online services organizations, people hosting Exchange, hosting SharePoint.
Danger,
hosting
all kinds of stuff, yeah.
We can talk about Danger offline, and I'll need a beer in my hand when I do. But then also you look at Azure and sort of our cloud platform facilities. And so Microsoft actually has to run the gamut of hosting our, and literally Microsoft has hundreds of internal properties. When you add up all the various types of services that we're offering, in addition to then wanting to bring on the outside world through Azure.
But am I right in understanding that this is essentially punting on the task of making those guys work together at some software layer and say, yeah, you could move stuff, but here's a very tight set of constraints that I will apply, and that will solve many of these many-to-many problems at a software layer. And you're just punting on that and saying that's not going to happen and that's off the table, and therefore we have to deal with this at the many-to-many layer 2 level. Is that right?
That's correct, because it reduces.
You don't have to answer that. Thank you.
One more.
Hi, Donnie Roisman from Pequip. Thank you very much. This looked really interesting. Two quick questions. One was, how often is that shim lookup happening to determine a path? Is it at the start of every flow? Is it more frequently than that?
So the way we're optimizing right now is at the start of every flow, because based on the number of the number of times a host server starts talking to another new server, it looks like that works out pretty well. Certainly you could aggregate and sort of have almost little routing tables so that a single entry could cover multiple hosts, but doing it per flow seems to work fine. Doing it per destination host works fine.
Okay. And then the environment that you had it's all layer 2, or is there any spanning tree going on as far as loop detection goes?
So we effectively have no layer 2 in a VL2 environment. We're using a layer 3 fabric in the network. The applications see themselves as being in sort of these VLANs, but the network is all L3.
Did you ever look at? I think I don't know whatever happened to woven systems. They had this V-scale.
Yep.
You guys looked at that. It looked like it was doing similar thing, but a layer 2, and it was keeping the work on the network, so you didn't have to move the work down to the server.
That's right. That's right. So their solution worked up to about 4,000 servers.
Got it.
And again, just didn't quite scale out beyond that.
Okay. Okay, cool. Thanks a lot.
Thank you. Okay, folks, we're on break now for about 25 minutes. We'll get started again at 11:40. We're running a little ahead of schedule, so we're actually going to pop in a couple more lightning talks. And Dave, it sounds like you got an announcement? Can we have the mic in the... Okay, so the other announcement is somebody left their glasses at Beer and Gear last night, and the registration desk has them, and so if you're missing glasses, go get them from the registration desk. Anyways, we're on break till 11:40, and we'll come back to some lightning talks. Thanks.